You people are coming from just out, or you are from bringing the desk? Ezra Chalk. Well, good morning, everybody. How are we? So we are continuing exactly from where we stopped, and we had progressed up to as far as the calculative bit of it, right? The numerical examples, but simply to make our viewer or a follower part of the class, we can try to a little move backwards. We say that we are basically looking at floating and what? Floating and sinking. Floating and sinking. And we said that floating and sinking are two conditions that happen onto a body we said that floating and sinking, these are basically two conditions that happen onto a body when placed in a fluid. Young girl, you are not supposed to be part of this class. Who else? Where is the other person? Who are you? Please go and study from Semakula's stream. Where is the other boy? Hey. There were three. Please, don't waste our oil, so you will follow her. So that is, I'm saying floating is when a body sits, if I'm due to lack of words, a body sits on top of a fluid in which it is immersed. And that immersion can in English be called partial immersion, right? That body will be partially immersed in a fluid and part of it is outside the fluid, then probably some small fraction. You people go to another class, you are it. Probably another fraction is in water. So this condition is what we called what? Floating. And then there is a condition when a body wholly, or when a body is wholly in a fluid, or wholly immersed in a fluid. That condition is what we called what? Sinking. We generally looked at some observations that bring about these two, or that can be explained by a certain principle. That we said that when any body is either partially or wholly immersed in a fluid, it experiences that force. That force is called upthrust. That body is immersed either partially or wholly in a fluid, it experiences that upward force. And that force that body experiences, according to the principle, it is equivalent to, according to the principle, upthrust equals to what? Weight of the fluid displaced. Weight of the fluid done what? Displaced. So in this case, human, this is senior 2. Please go, don't disturb me here. Yes, mister. Good morning, sir. You yourself.
First clean up their portion there, go to the other side.
I understand.
So they have finished.
With who and who, because not all of them. Let them first come. They enter once. There are 5 people, 7 people.
Yes.
Let them come first, they enter once.
Yes.
Okay. After they have come, you let me know. So this is according to the principle called Archimedes. But now, also mathematically, you man, I will slap you. Well, can you leave this place? Can you go? I said, can you go? So that is according to Archimedes. But then there is according to mathematics. According to mathematics, when you weigh this body outside water, you will get its actual weight. When you weigh that body outside water, you will get its actual weight as weight WA. But when you take the weight of this body, when inserted or when immersed in a fluid, you will get what we called what? What we defined as apparent weight. And that apparent weight is what we said that suppose we have taken the weight of this body in water, that weight we are going to record it as weight W. And we all agreed and confirmed that the two weights cannot be the same, isn't it? One weight is greater than the other. Is it the case? So if this weight or these two weights are not the same, then it means there is what we call apparent loss in weight, right? So the apparent loss in weight, the change in weight is going to be the weight in air minus the weight in water. Calculations and experiments will show that this upthrust a body experiences equals the apparent loss in weight. Are we together? The apparent loss in weight of the body. Now, our calculations that I am going to continue with are simply rotating around all these facts. If you are given the weight of the displaced fluid and you are asked to find the upthrust force, you simply equate the two. That weight equals the upthrust force. Are we together? But if you are given the weights, the actual and the apparent weight, the subtraction of the two will give you the upthrust what? Force. Now the remaining work, according to my daughter here, were algebraic gymnastics, where we said that now, if we again refer to the senior one physics, physics, in one of our experiments where we determine the volume of an irregular object, we said that the volume of the object is equivalent to the volume of the displaced what? The volume of the displaced fluid or water. Are we together? According to our senior one, we said that if you want to measure the volume of an object using a method that we defined as either displacement method or an Eureka-Can method, the volume of this object that is in the water is equivalent to the volume of that water that was displaced. So again, if we apply all those dynamics, we shall have the volume of the object equals the volume of water. The volume of water. So that will imply that, again, upthrust being or equaling to the weight of the displaced fluid, and the same upthrust equaling to the weight, the apparent loss in weight, it will imply that the apparent loss in weight equals the weight of the displaced what? Equals the weight of the displaced water or the fluid in general. Now, again from here, we can put in the other physics I've talked about. This weight equals mg. Are we together? This weight, or the apparent loss in weight, equals this weight, which weight equals to m what? But this is the mass of the displaced fluid. So it's going to be, from again our senior one mathematics or physics, mass of the substance equals density of the substance times the volume. So substituting this here, we shall have our apparent loss in weight equals rho v, rho v, rho vg. So these are what we are going to continuously apply in our subsequent calculation. So calculation next. Which one did we stop on? 1. Let us go to 2. One volunteer can read us through problem 2. A volunteer, Evelyn. A volunteer has failed to show up. The rest you simply keep quiet and follow what you noted. Yes. Yes. Calculate. Upthrust. Weight of displaced water and volume of displaced water. Ladies and gentlemen, what do we know? Solution. What do we know? The actual weight, or the weight in air. It is 20 newtons. 2. What else? Weight in water is 15 newtons. Do we know any other thing? Question Roman 1 is asking for upthrust force. But according to the facts we know, number 1, upthrust either equals to the weight of displaced water. Question, do we know the weight of displaced water? Do we know the weight of displaced water? Then we go to alternative 2. Upthrust equals to the apparent loss in weight. Do we know the apparent loss in weight? We don't know it, but can we get it? So apparent loss in weight equals what, ladies and gentlemen? Actual weight, or weight in air, minus weight in water. So our apparent loss in weight equals 20 minus, and our apparent loss in weight equals 5 what? Therefore, upthrust equals 5 what? Newtons. Roman 2. Weight of displaced what? Which we are going to denote as W subscript D. Weight of displaced water, according to Archimedes' principle, weight of displaced water equals to what, ladies and gentlemen? Upthrust. Therefore, upthrust equals weight of what? The displaced fluid. So our upthrust is what? Therefore, the weight of displaced water equals to 5 what? Newtons. And Roman 3, volume of displaced what? Water. Volume of displaced water. Now we are going to come back here to this mathematics. That if weight equals the mg, weight equals to mg. So our weight of displaced water equals m what? mg, but mass of displaced water, can you wait to write? You write later. But this, if this is weight of displaced water, it means even this is mass of displaced water. Turn around. So if this is mass, so we shall have weight equals m of displaced water times g. Of course, g is a constant. Are we together? Therefore, but mg is going to be according to rho and v. M equals density of the displaced water times volume of displaced what? Water. So we shall have M equals rho d, this is MD, right? Equals rho d times VD, where VD is the volume of the displaced water. So we shall have our weight of displaced water equals rho d VD times what? Times G. So our weight is what? 5 equals, what is the density of water? 1000 times the volume of water. It's what we are looking for, VD, then times G, which is 10. So 1000 times 10, 5 equals 10,000 V what? So to get D alone, what do? We divide both sides by 5 by 1000 by 10,000. So divide both sides by 10 what? 10,000. So pull out your computers. Therefore, the volume of displaced water is again 0. 5. These are meters what? These are meters what? Meters cubed. Somebody is saying meters squared. Can you take note? Yes. Ezra. So there are quite many examples, ladies and gentlemen. There are quite many examples that I cannot just finish in 80 minutes. So can we make an agreement that you can try the rest? Yeah? Can we make an agreement that you people can try the rest? What is wrong with number 4? Huh? So I try one more. Which one? Okay, let us agree. Which one should I try last? Democracy. How many are saying number 3? So I'm seeing the majority are looking at number 3. Let's try number 3. Who is that one reading? Please go on. Go on. Are you sure that is meters squared? Is it where it stops? Solution. Again, I am not going to go off track. As I usually tell you, number one, begin by analyzing, extracting out what you have or what you know, and then what you're supposed to find or what you don't know. Then think about how the two are related. Of course, there must be, by physics principles, a way how these two are related. Even if the relationship is not standard. Take an example. It may not necessarily be direct that what you are looking for is a standard quantity, but it is related to all the information you have by certain principles. Meaning, if you put all those principles in practice, definitely you are going to come up with what you don't know. So what do we know in this case, ladies and gentlemen? The mass of what? Of the block. So let's call it M subscript B. The mass of the block, Joan Mwisho, this is 3.0 exponent. Once you say exponent, you shall have combined the times 10 to power. Meaning, when you say exponent, you simply quote the power. So it is 3.0, repeat after me, 3.0 exponent 3. All of you repeat, 3.0 exponent. That is science or scientific language. So the mass of the block is 3.0 exponent what? Kilograms. This body is heavy, because if we are to put this into the normal figure form, this is going to be 3,000, around 3 tons of the block. So this block has a volume of, what is the volume of the block? Has the volume of the block is 1.2 meters cubed, ladies and gentlemen. But it is totally immersed into a fluid of density. Now this density is not density of the block. Are we together? Yes. Because in any case, if we know the volume of the block and the mass of the block, can't we find the density of the block? We can find the density of the block. So the density provided to us is the density of the fluid. We are calling it rho F or rho subscript F. So this one equals to exponent what? Exponent 3 kilograms per meters cubed. Is it to power? It's actually to power a negative 3, isn't it? Calculate or find the weight of the block in air. We are supposed to find the weight of the block in what? In air. We are supposed to find the weight of the block in what? In air. But here, just like I've mentioned in the preamble at the beginning of the problem, that it may not necessarily be direct that you are going to say now the weight of the body in air equals mg. But we are going to do it in a reverse manner. We are going to do it in a reverse, quoting all the principles we know about the weight of a body in what? In air. Are we together? Quoting all the principles that we know that can lead us to calculating the weight of the body in air. Yes. It is 10 to power 3. Then this person is confusing me. Thank you. Thanks for the observation. So we are going to now run reverse words, right? We are going to run reverse words. One thing we know is that the weight, one thing we know is upthrust equals the apparent loss in weight. Is that one the fact? Is it true? Is it going to help us? Please don't just respond. Is it going to help us? The answer is no. So we go on, and we know that the apparent loss in weight equals weight in air minus weight in the fluid. This one has a component of the weight in air, but is it going to help us directly? No. Still, we also know that the apparent loss in weight equals the weight of the displaced fluid. Is this one also a fact? Is it a fact? Is it a fact? I'm asking, is it true? It is not. Is it true? Where are those that are saying no by show of hands? I am asking, is this statement correct? I am getting the voice of a boy saying, no, I will chase all the boys out. Once again, is this statement correct? Where are those that are not sure? Put up your hands. Lastly, is this statement correct? Yeah? All of you go and open your Archimedes principle. Will you read for us the principle? Again? When a body is rolling over, when anybody, including your body, is wholly or partially immersed in a fluid, it experiences an upthrust, which upthrust equals to the weight of the body, weight of the fluid displaced. I asked you, is this statement correct? Eh? Then what about this? Eh? It's not. The weight of the fluid displaced does not equal to the apparent loss in weight of the body. Obvious. They are not the same? Or you are confused? Is it correct? Now you see, you people, you do not revise. Didn't we say that upthrust equals weight in air minus weight in water? Is this correct? Yes. How did we define this? Didn't we say that this is the apparent loss in weight? Yes. So if the upthrust equals to the apparent loss in weight, and the same upthrust equals to the weight of the displaced fluid, didn't we say that these two are also the apparent loss in weight equals to the weight of the displaced fluid? Obvious. Didn't we say this? Eh? Now, I'm asking, is this correct?
Yes.
All right. Now, if this one is true, and this one is also similarly true, then we can apply this again in the reverse order until when we achieve some two things, the apparent loss in weight and the weight of the displaced fluid. Then we substitute here and get the actual weight in what? I mean in air. Now, the apparent loss in weight, if you've all now, or if all of you are convinced that the apparent loss equals to the weight of the displaced fluid. So this is going to be mg, right? The weight of the displaced fluid is going to be m what? Mg. Are we together? But then mg is rho. We are dealing with now the displaced fluid. Are we together? Yes. So this mass is mass of the displaced fluid. Are we together? So the density is also going to be the density of the fluid. Are we together? Then times the volume V. Volume of the fluid, F times G. Are we together? Wait, young girl, look here. Are we together here? Then the density of the fluid is known, right? Are we together? Then the volume of the fluid is not known. Is it the case? But we know that the volume of the fluid will be the same as the volume of the object, because when an object is put into the fluid, it will displace unequal volume of the fluid. So we can substitute for VF with VB. Are we together? Using displacement method, when you put any object into a fluid, it will displace the same volume of the fluid, or it will displace its own volume of the fluid in which it is inserted. So we shall have now the density of the fluid is 2.0 exponent 3, right? Times the volume of the fluid, which we are saying that it is the same as the volume of the object, which is 1 point, and then times G. What is G? 10. Joan Mwisho, are we together? The mathematics gives you a hard time. I know you end up dozing and yawning when we have a lot of figures. So compute this. I beg your pardon? You man, this is 2000. Trace, where is your computer? Where is the computer? Tracy. Where is yours? And you? If you don't have a computer, you put up your hand. I'm going to order for a stick. You don't have one. Put the head here. Where is yours? Bring it. Where is yours? Joan, is it yours? Wake up. And you? Pull it out. If it is not there, I'm going to kick you. Where is yours? You left it intentionally. Where is yours? Shebuya, where is yours? No. Where is yours? Where is yours? My friend, where is yours? Wake, I want to slap on the cheek here. Making noise. What do we get here? 24,000. What are the units here? What are the units of weight? Newtons. So this is the apparent loss in weight. That is the apparent what? Loss in weight. But the question is asking for the weight in air. The weight in what? Of the what? Of the block. Now, if this is the mass of the block, if this is the mass of the block, what is the other way of finding the weight if you know the mass? What is the other way of finding the weight given the mass? Labera. Weight also equals mg. So the weight of this block in air equals to its mass in air times what? Times g. And what is its mass in air? What is its mass in air? So which means that weight in air equals 3.0 times 10 to power 3 times what is g? 10. So we shall have our weight in air as 3.0 times 10 to power 4 newtons. You can check if you doubt. If you had a calculator, you wouldn't be wondering. Which is 3.0 times 10 to power 4. You also want to prove from a calculator that is not yours. If you want to prove, make sure that you prove from a calculator that belongs to you. Yes? Which answer do you have?
One in the handout.
It is what? 6 or 30,000? Roman 2 is asking for the weight of the fluid in what? Weight of the display. Roman 2 is asking for weight of the block in the fluid. WF. W what? WF. Now, from the fact that the apparent loss in weight, equals weight in air, which is the actual weight of the block, minus the weight in the fluid. Do we have the apparent loss in weight? Do we have the apparent loss in weight? Yes. We have calculated it. All right? Then we have the weight in air, meaning we can substitute in this equation here. So we shall have our apparent loss in weight equals the weight in air minus weight in the fluid. The apparent loss is 24,000, right? Equals the weight in air is 30,000, right? Minus the weight in the fluid. Have you confirmed? Is it 30,000 the same as 3.0 exponent 4? Yes. So now the remaining work here is algebraic gymnastics, right? So taking this on this other side or taking this the other side, then I bring this way, mathematicians. When this weight of the fluid crosses an equal sign, Tracy, it becomes a positive when it comes this way. But now when I carry this figure, 24,000, and I take it on the other side, it becomes a negative. So convince yourselves that the weight in fluid equals 30,000 minus 24,000. Therefore, our weight in the fluid will be 6,000 what? Neutrons. Can my students try the rest of the examples? Floating. 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 Yeah. Yeah.
Yes.
The instructions are you are going to do the rest of the examples and the exercise. I'm not seeing anything hard there. No, the time does not matter, but just know you are going to do that work. Floating. My daughter here, can you take us through what floating is? You are delaying. It seems you don't have the work. Yes. Yes. Young girl, read the words the way they are, not what you want. The object does not think, sinks. Yes. Absolutely. Continue. Sorry. Ladies and gentlemen, floating is in English different from sinking. However, even sinking that we are talking about, it is different from thinking, Hajar. To think is to, use your head. Think about something, Yesterday I had an interaction with an old man that side. And he was trying to tell me do you people know how to play chess? Yes. Very few, I think. Chess is a military game. A military game that teaches militants to think. But those who know how to play it, you will bear me witness that if you are to make one move, if it is your turn to make a move, of course you are supposed to make one move, isn't it? But you have about 20 alternatives, about 20 moves to make, but you are supposed to decide on one out of 20 that you are going to make. But the interesting bit of it is here, that before you make that move, you must think of what is going to be the opponent's move. Can you imagine? Before I come here to teach, I must think, what are you going to actually put forward then? Because there is a possibility of me coming here and none of you turns up. There is a possibility of me appearing here and probably your brains and your minds are not here. And that is the possibility with the biggest chances. Because as even I'm talking here, the other man's minds are very far. If you ask him what I've just said, he cannot tell you. So again, the interesting bit, John, is you not only think about what the opponent's move is going to be. Remember, you are supposed to make one move. You are supposed to make one what? One move, but you have 20 of them. And out of the 20, you must think of, after I've made this move, what will the opponent now make as a move? And you don't stop there, Evers. You again now think of what you will make as the other move. That is why chess is very difficult. A lumpen cannot play chess. Neither can a buffoon play chess. You must be good at what? Thinking. I always tell people, where we are now in Uganda, we need thinkers. You must think. But if your biceps and triceps are strong, my friend, you are not going to survive. If you have only stronger biceps and triceps with a weaker thinking capacity, the Uganda we are in today is going to leave you. Maybe you only need to stay in Mbarara and other cities away from the capital. Yeah. But if you are to survive in my village, you know my village? My village is the capital city of this country. If you are to survive from my village, you must be a great what? A great thinker. So we are saying that a body floats. My daughter has told us that a body floats if its average what? Density. If the density of the body is less than the density of the fluid, that body is going to, in Luganda we call it kutengeja. It's going to kutengeja on top of the fluid. However, when an object is placed in a liquid, it is acted upon by, number one, I told you that when a body is partially or wholly immersed in a fluid, its weight acts downwards. Are we together? When a body is, even if partially or wholly immersed in a fluid, its weight is the one that is dragging it downwards. But also the liquid is saying, you cannot go through me just like that. It gives an equal but opposite what? Force. Which force we are calling the what? The upthrust. Now, if the weight of the body is greater than the upthrust, ladies and gentlemen, that body is going to experience what? Sinking. It's going to sink into the water. But if the two are equal, what is going to happen to the body? That body is going to float on the fluid. So that is what we literally have as this body is floating. That is if it is not completely dipped into the fluid. So the data is telling us that the object sinks in the liquid if its weight is greater than the upthrust. Remember, we looked at the resultant force on a body. When a body is being acted upon by a number of forces, or two forces in opposite directions, and the one in a particular direction is greater than the opposing force, then the body will move to the direction of the greater force. However, the body floats in the liquid if its weight is equal to the upthrust. The body will not move downwards, that body will not move upwards. It will be there, floating, enjoying the buoyancy or the upthrust force. When you go to beaches, especially, do you have a beach in Mbara?
Yes.
Which beach is that? When you go to beaches, you find people, especially young ones like you, they get tubes. You know a tube? And they put it in their waist and you find them floating, of course, on top of water. This tube, it also facilitates the fact that the average density of you two, the tube and your body, are going to be less than the density of this water. And at the end of the day, you are going to be floating. And ideally, that is how they train young ones, our children in nursery schools, how to swim. Because now when you float, they can take you through the principles of how to move the legs down there. Then time comes when you have now mastered the techniques of moving the legs, then they can take away the tube and they show you how to move the hands. And at the end of the day, a kid learns how to swim. Hajar, do you know how to swim? Now you go, Hajar, if you don't know how to swim, go and apply these principles here. Go and dip yourself into Riveriz. Is it Riveriz? All right. The object floats if the object floats in the liquid if its weight is equal to the upthrust. Therefore, the apparent weight must be zero. A body floats on the fluid when its apparent weight, we say that the apparent weight is the weight of a body, not before John. The apparent weight is the weight that a body gives when you measure, and this body is in a fluid or in water specifically. If you get a body, put it in water, then you get a spring balance, measure the weight of that body. That weight you will get is what we are going to call the apparent what? Apparent weight. So the apparent, yes? What is it, young man? You go to the sick bay. You know, the challenge with my boys is that they are strong men. I've never seen in this school, I'm going to make my second year in September, but I've never seen a boy collapsing. But ladies collapse like nothing. Yes, Wanadan. Good morning. So I give credit to them. I think they handle their health seriously. But now, these girls, tomorrow you find the Kajo and people are carrying her, breathing like a running dog. So therefore, the resultant force on the object or the apparent weight of the object must be what? For a body to do what? For a body to float, not to float. For a body to float, its apparent weight must be zero, or the resultant force on that body must be zero. However, when a cork is held below the liquid surface, ladies, listen. Do you know a cork? When a cork is held below the liquid surface, e.g. water, and released, how many of you has ever done this or has ever experienced this? When you get, let us take an example of a cork is a lid on a flask, a vacuum flask. Yes.
So you have said for a body, for the apparent weight to sink in water, it must be zero.
For a body, you know, Joan, you're absent-minded. I repeat, for a body to sink, for sinking, the condition for sinking is the actual weight of a body. The actual weight of a body must be greater than the upthrust. Right? Alternatively, the density of a body should also be greater than the density of the fluid. Basically, these are the two conditions for sinking. Now, for floating, it is the actual weight of a body equals to the upthrust. Are we together, John? and the density of the body should be less than the density of the fluid. These are the two conditions for floating. Now ask your question. Good. So, however, when a cork is placed under maybe water, because now we cannot give other particular examples. When a cork, a cover of a flask, is by force dipped or pressed into the liquid and you hold it from the bottom, ladies and gentlemen, what happens if you release it? It will come up, but at a very fast speed, which will mean that the upthrust is greater than the weight of that body. NB, Tracy, can you read us the NB? By Archimedes' principle. That one we have talked about it several times, and it is what is popularly being used in our examples and the exercise that you are going to do. That the upthrust equals the weight of displaced fluid. Continue. Yeah.
For a floating body, its weight is equal to the weight of displaced.
For a floating body, I have already answered this question for John. That for a floating body, the weight of the body is equivalent to the weight of the displaced fluid. The weight of the displaced fluid. That drives us to the law. The law of flotation. The law of flotation. The law of flotation. I told one of your friends who approached me, asking me how best can I revise physics, and I understand it. I was like, look at a concept, a minor concept. Think about what is its definition, if it has. Of course, most of the concepts have definitions. 2, look at the SI unit, of course, of the concept. If the concept is a quantity, is a measured quantity. Then if it is again a measured quantity, still it has the mathematical expression. Talk about pressure, talk about force, talk about all those things that can be defined and calculated. Then look at, does the concept have a principle, a law, or a theory? It is also what you are supposed to revise. Have the principle on your fingertip. Anything that has a principle or a law, it has a verification, an experiment to verify that principle, that law, or the theory. Also revise it and make it part and parcel of you. And then look at the calculative examples of the principle. Won't you have revised a concept? I'm asking, if you look at all those that I've talked about, won't you have the principle at hand? Eh? You will. Now, any law, ladies and gentlemen, you know I'm not a lawyer. I'm not a legal personnel. But I am a physics lawyer because I know almost all the laws of physics. Yeah. I am a physics lawyer. I know all the laws of Professor, quote the laws, master the laws, and then you will move on. Evers, how does the law, what is the statement of the law?
States that a floating body is placed at its own weight on the floor.
Repeat again. Read what is in the law, not what you want to be part of the law. Yes? Yeah. Evers, once again, you stand up, breathe in and out, then read the law. If you remember, the note Tracy read before we went to the law. It says that therefore, for a floating body, its weight equals to the weight of the displaced fluid. And this conclusion was also made by quoting whose principle? Archimedes' principle, who says that any body, wholly or partially immersed in a fluid, it experiences an upthrust, which upthrust equals to the weight of the displaced fluid. But now Archimedes is looking at a body that is either sinking or tending to sink in a fluid. But now the law of flotation comes in and particulates, or it particulates the Archimedes law by saying that for Archimedes looking at generally sinking and either at or attempting to sink. But this one is being specific, looking at what if the body merely floats. So that law says that for any body floating on top of the fluid, its weight is equivalent to the weight of the displaced what? To the weight of the displaced what? Fluid. Which weight was observed by Archimedes that weight equals to the upthrust force. So the mathematics part of it is weight of the body equals weight of the displaced fluid. This is the mathematics part of the law of flotation. Now the remaining work according to the handout or according to the book is algebraic gymnastics, where how do we find the weight of the body? Are you seeing that? Weight of the body equals mg. So mb times g equals m of the displaced fluid times what? Times g. But g coexists on both sides of the equation. So if I divide both sides by g, and this one goes with that, so I remain with mass of the body equals mass of the displaced fluid. But this one only applies when a body is floating, ladies and gentlemen. The moment a body is not floating, the body is sinking, then we quote Archimedes' principle. Are we together? So then from here, again, we know that what is the mass? How do we get the mass of